Unit 2, Lesson 6, Part 3. We are now going to discuss higher order derivatives. We will come back to these quite often in the future, but this is our introduction to them. So, topic 3.6, calculating higher order derivatives. Did you realize it's possible to take the derivative of a derivative? We will need this ability when we study particle motion, and those of you who are taking physics will see this probably in the very near future if you haven't already. So we start with our position function, which is normally defined as s of t. The derivative of the position function is the velocity function. And then you can take the derivative of the velocity function to get your acceleration function, which turns out to be the second derivative of the position function. Now what you'll notice is that when we took the derivative, we have that little hash mark there, the prime mark, both for the position and then for the velocity. But now when we look at the acceleration being the second derivative of the position function, we have a double hash mark. So we're going to talk a little bit more about that and the notation at this point. Okay, so just laying out the first four derivatives that you can take. Not all functions will have four derivatives. Some of them only have a couple. It depends on the function itself and what the value of the derivative is. It may get to a point where you have a constant for a derivative, so its next derivative will be 0, so you won't be able to take the derivative anymore. But for those functions where you can take more than 2 or 3 derivatives, here's the notation. So what we do is we add a prime mark for the first 3. So your first derivative has 1 prime mark, your second derivative has 2, and then the third has 3. Then after that, we just don't want to have to count all those hash marks. So we start putting little numbers up there. So fourth derivative would have a 4, fifth derivative would have a 5, and so on. And that goes for our f of x notation too, where we use the prime marks. Once we get past 3, we use the numbers. And for our dy dx notation, we just start putting the numbers right away. So we have our dy dx, and then we go, notice that we're taking the second derivative with respect to x twice. So in the bottom, the number goes with the x, because that's the derivative we're taking. That's the independent variable. That's the variable we're taking the derivative with respect to. Okay? Now we'll see later on that it's possible to have a multi-variable function where we can take the derivative with respect to one variable and then take the derivative with respect to another one. So that's why we want to be careful that in the denominator, the derivative number is with that independent variable that we're taking the derivative with respect to. And that goes for our formal notation as well. Okay, so let's do a couple of these. So example 6, for each of the following, find the stated derivatives. So for part A, we have to find the second derivative. So that means we're going to take our function and we're going to take the derivative twice. So f prime of x is going to equal 9/2 x squared plus 10x minus 6, and then the 1 will be 0. Then we just take the derivative again, and we'll have the answer to this problem, the second derivative. So we get 9x plus 10. So that's our second derivative. For letter B, we're taking the fifth derivative. So we're going to take the derivative 5 times. So we'll start with f prime of x, and we'll get negative 12x to the third plus 21x squared minus 10. Now for the second derivative, we're going to have negative 36x squared plus 42x, and then the 10's derivative will be 0. The third derivative is going to be negative 72x plus 42. The fourth derivative is going to be negative 72. And then finally, the fifth derivative is going to be 0. because the fourth derivative is a constant. Okay, now, for one like C and D, what you have to do is find the pattern, because you don't want to take the derivative 32 times. Now, what we do know is that the derivative of sine with respect to x is cosine x. And then when we take the derivative, I'm just going to use this notation. The derivative of cosine, we're going to get negative sine x. Now we want to keep going, so we're looking for a pattern. So what I'm going to do is, at some point, I should get back to positive sine x. So let me continue. So when I take the derivative with respect to minus sine x, I get negative cosine x. And then when I take the derivative again of negative cosine x, I'm going to get sine x. So I'm back to where I started. So we had the first derivative, the second, the third, the fourth. So I'm going to go through that pattern over and over again, and I'm looking for the 32nd one. So I know that the 32nd derivative is going to take me back to where I started from. So d32 dx 32 of sine x is going to equal itself sine x. So when you have very large derivatives like that, try to find the pattern. Okay, so for the next one, 867, that's a weird derivative. So we want to find where the pattern is for that one. Okay, so for 867, what you want to do is, like in letter C, find the pattern. So let's first see how we're repeating ourselves here. So what we're going to find is that, let's do the first derivative of cosine. Y prime is going to equal negative sine x. Y double prime is going to equal, excuse me, negative cosine x. Y triple prime is going to equal positive sine x. And then the fourth derivative is going to equal cosine x. So I see I'm back where I started after 4 derivatives. So the question is 867 is an odd number, but let's take a look here. So if we take 867 divided by 4, and as I said, it's odd, it's not going to go in evenly, but what you find is the closest number of times is 216 times, with a remainder of 3 more times. So that would mean at derivative 216, so y of 216 would be cosine x. So I'd be where I started. And then I have to take the derivative 3 more times. 1, 2, 3. So that means this is where I would end up. So I can say that y 867, well, I should put I'm going to do it 216 times. So this should actually be 216 rotations. So this is actually 864. So derivative 867 is going to be sine x. And let me just go through that again. I'm sorry. So I'm going to do this rotation. This is the number of rotations of 4. So that would be 1, 2, 3, 4. I'm going to go through that process 216 times, which means that's a total of 864 derivatives. So I still have to do it 3 more times, which would be 1, 2, 3. So that's where this would end up here. Okay, and then finally, one application problem dealing with our velocity and acceleration, which will lead us into the last section of this unit, which is about velocity and rates. We have a potato launcher that fires a potato downward from the top of a 112-foot building. The potato hits the ground in 2 seconds. So find the instantaneous velocity of the potato. The position function is given, so S of t is negative 16t squared plus VOT plus 112, where distance S of t is in feet and time is in seconds. So what I need to find is the initial velocity. So here's what I know. I know that the potato is going to hit the ground, so that means that its height is going to be 0, and that happens at 2 seconds. So I can substitute in 2 into the equation and then solve it for VO. So when I do this, I get 0 equals negative 64 plus 112 plus 2 VO. So putting these together, I get 0 equals 48 plus 2 times the initial velocity. So the initial velocity, 2 times the initial velocity, is going to equal negative 48. So the initial velocity is going to be negative 24. And what that tells me is the direction. That negative sign tells me the direction, and it is downward, so that's what I have. So my initial velocity is going to be negative 24 feet per second. Or you could say, if you wanted to write in a sentence, the initial velocity is 24 feet per second in a downward direction.